Welcome back, everyone. Today we're expanding your understanding of vectors from two-dimensional into three. Since physical forces and velocities are not confined to the plane, so it's natural to extend the concept of vectors from 2D space to three-dimensional space. If you know how to add, subtract, and multiply vectors by a scalar in two-dimensional space, you're more ready for three-dimensional vectors than you might think. If not, I suggest you watch my vector operation video before watching this video. In this video, we'll explore vector operations in 2D, including addition, subtraction, scalar multiplication, dot product, finding the angle between two vectors, and introducing something new, the cross product. In 2D, vectors have two components, x and y, but 3D vectors, on the other hand, have three components, x, y, and z. Vector u in component form would be written as our first component, print comma, second component, comma, third component. Now, vector u in standard unit vector form would be written as our first component times I plus our second component times j plus our third component times k, where vector I is defined to be the vector 1, 0, 0, and vector j is defined to be the vector 0, 1, 0, and vector k is defined to be the vector 0, 0, 1. Now let's do some practice problems working with three-dimensional vectors. Now, given that vector v has the initial point 2, 4, 1 and the terminal point 3, 5, 2, we want to find the component form of vector v. Now remember the component form is found by taking your terminal point minus your initial point. So the x component of vector v in component form would be equal to 3 minus 2. Our y component would be our terminal y minus our initial y, so that'd be 5 minus 4. Therefore, the z component would be our terminal z minus our initial z, or 2 minus 1. So we would come up with the component form for vector v is 1, 1, 1. Now let's find the length or magnitude of vector v. Remember, those words are interchangeable. Now, in order to find the magnitude of a vector, remember we take the distance formula. And if it's in vector form, our magnitude is equal to the square root of our first component squared plus our second component squared plus our third component squared. So our first component is 1, so we have 1 squared. Our second component is also 1, so we have another plus 1 squared. And likewise, our z component is 1. So we have plus 1 squared. 1 squared is 1, so we have the square root of 1 plus 1 plus 1, which is 3. So our magnitude or length of vector v is equal to the square root of 3. Let's look at part C, where it says find the unit vector in the direction of vector v. Now remember, our formula to finding that unit vector in the direction of a given vector is equal to our vector v divided by our magnitude of vector v. Now, we've already found all this information in parts A and part B. We found that vector v is defined by the components 1, 1, 1. And we found in part B that the magnitude of vector v is square root of 3. So this is the same as taking 1 over the square root of 3 scalar times by the vector 1, 1, 1. Remember, to multiply by scalar, you just distribute the scalar to each component. And so I'm multiplying each of these ones by 1 over the square root of 3, and that gives us our unit vector of 1 over the square root of 3, comma, 1 over the square root of 3, comma, 1 over the square root of 3. Now you might need to rationalize this depending on your teacher's preference. Now, for example 2, we want to find the following operations, given that vector v is now the vector 0, 3, negative 2, and vector u is the vector 4, negative 2, and 2. So part A, we're going to find 3 times vector v minus 2 times vector u. To do that, we're going to do order of operations, meaning multiplication comes before addition or subtraction. So that means we have 3 times vector v. Vector v is the vector 0, 3, negative 2. Minus 2 times vector u, which is the vector 4, negative 2, 2. Now we want to do multiplication first, so I'm going to multiply each component of the first vector by 3 to get 0, 9, and negative 6. And I'm going to keep the negative here, and I'm going to multiply every term in vector 2 by 2 to get 8, negative 4, and 4. And now I'm going to do subtraction. So 0 minus 8 will give us a negative 8. 9 minus a negative 4 becomes 9 plus 4, or 13. and negative 6 minus 4 gives us negative 10. So 3 times vector v minus 2 times vector u is equal to the component negative 8, 13, negative 10. For example B, we're going to find the dot product of vector v and vector u. To find the dot product, remember we take our first component of vector v, times it by our first component of vector u, plus the second component times by the second component, plus the third component times by the third component. So in this case, if I wanted to find the dot product between vector v and vector u, I would take my first component of vector v, times it by my first component of vector u, so that's going to be 0 times 4, plus, now I'm looking at the second components of each of those vectors, so that's going to be 3 times a negative 2. And last, I'm going to take my z components, and I'm going to have negative 2 times 2. And then I'm going to do multiplication first, so that's going to 0 minus 6 minus 4, and add that together and gives me a negative 10. So our dot product of vector v and u is negative 10. Now we want to find the angle between vector v and vector u. To do this, we need a new formula. Now the angle between is the cosine of theta is equal to the dot product of vector u times vector v divided by the magnitude of vector u times by the magnitude of vector v. So this is very similar to our angle between two vectors that we learned with two-dimensional objects, but now it's with three. We have a slight change. So first thing we need to do is we need to find our dot product, which we found in part B, is equal to negative 10. Then we need to find the magnitude for vector u and the magnitude for vector v. Let's start with the magnitude of vector u. Remember, the magnitude is equal to the square root of the square of each component. So the magnitude of vector u is going to be equal to the square root of 4 squared plus the negative 2 quantity squared plus 2 squared. And that's going to give us the square root of 16 plus 4 plus 4, or the square root of 24. I'm going to not simplify this yet. You can simplify it at any time if you want to. Okay, we're going to repeat this process to find the magnitude of vector v, which is going to be equal to the square root of each component squared, the sum of each component squared. In this case, that's going to be 0 squared plus 3 squared plus negative 2 quantity squared, which is going to be equal to the square root of 0 plus 9 plus 4, or the square root of 13. Now I'm ready to use my formula for the angle between two vectors. So I'd write the cosine of theta is equal to the dot product between vector u and vector v, which we found in part B to be equal to negative 10, times by the magnitude of vector u, which we just found to be the square root of 24, times by the magnitude of vector v, which we found to be the square root of 13. So that's equal to negative 10 divided by the square root of 24 times 13. You don't even have to bother multiplying these together because I want to simplify now. And so I want to figure out, is any perfect square that will factor into any of those terms? Well, 4 times 6 gives us 24 times 13. So I can simplify this down to the square root of 6 times 13, which is 78. And then I can cancel out a 2 in the numerator and 2 in the denominator. And I can write my cosine of theta to be equal to negative 5 over the square root of 78. But I am not done. I need to find theta. So if cosine of theta is equal to negative 5 over the square root of 78, I therefore can conclude that theta is going to be equal to the angle whose cosine is negative 5 over the square root of 78. Punching this into my calculator, make sure I'm in degree mode, because unless specified otherwise, we're going to use degree mode. I would get an answer of 124.48 degrees is the measure of the angle between these two vectors. Many applications in physics, engineering, and geometry involve finding a vector in space that is orthogonal to two given vectors. The cross product is a product that will yield such a vector. Cross products are conventionally defined and calculated using the standard unit vector form. To calculate vector u cross product with vector v is to use the determinant form with cofactor expansion for 3 by 3 determinants. The cross product technically is not a determinant because the entries of the corresponding matrices are not all real numbers, but the process is the same. So we're going to talk about determinants a little bit in this section. Here's the official definition of the cross product. if we have vector u and vector v defined in standard vectored form, then the cross product vector u times vector v is equal to u2v3 minus u3v2 times by the vector I plus u1v3 minus u3v1 times by vector j plus u1v2 minus u2v1 times a vector k. And I'll be honest with you, I never memorized this formula because there's a lot of sub 2s and sub 3s and sub 1s and I could never get them straight. So I used the determinant that we learned in algebra class. So I'm going to show you with this example how to find the cross product using just determinants. But if you love memorization, feel free to use this formula in doing your work. Given that vector u is I2j plus k and vector v is 3i plus j plus 2k, let's find the cross product of u times vector v using 3 by 3 determinants. So first we're going to set up our first row, which is going to be our vectors I, j, and k. And our second row is going to be our first function or first vector that we are multiplying by. So in this case, vector u, and we're just going to list the coefficients. So under I list the coefficient of I, under j, the coefficient of j, and under k, the coefficient of k. Third row is going to be vectors v coefficients, which will be 3, 1, and 2. Now, I'm going to do the shortcut to figure out the 3 by 3 determinant. So I'm going to copy down this I column. Next, I'm going to copy down the j column. And if you've never done 3 by 3 matrices, this method is really easy. What you're going to do is you're going to take the diagonal down and we're going to multiply everything in that diagonal together. So that will give us 4i. Then the next diagonal down, and that'll give us a 3j. And our last diagonal down, because I don't have any more on the bottom here, will give us 1k. Now I'm going to take the diagonals up. 3 times 2 times k will give us 6k. 1 times 1 times I will give us I. And 2 times 1 times j is positive 2j, so we're going to add 2j. Now the rule is that you're going to take the diagonals down minus the diagonals up. The sum of the product of the diagonals down minus the sum of the product of the diagonals up. So in this case, that would be 4i plus 3j plus k minus 6j plus I plus 6k plus I plus 2j. Then let's distribute that negative to the second group of parentheses and group our like terms. So 4i minus I is going to give us 3i. And then 3j minus 2j is positive 1j. K minus 6k is negative 5k. And that is our product. That is the cross product of vector u times vector v. Okay, now let's take vector u times vector v times vector u. So let's see if the order in which you do the cross product makes a difference in our answer. So again, set up our first row to be our vectors I, j, k. Second row is going to be our first vector. In this case, is vectors v coefficients, which would be 3, 1, 2. And our third row is going to be vector u's coefficients, which would be 1, 2, and 1. Make sure they're in the correct order of I, j, k. Then I'm going to copy down my column I, and I'm going to copy down my j column. And then I'm going to take the product of our diagonal down. And this first one, that'll give us 1i. And then the next diagonal down, 2 times j times 1 will give us positive 2j, so plus 2j. And our next diagonal down, k times 3 times 2 is positive 6k, or plus 6k. And then we take our diagonals up. 1 times k gives us k. Next diagonal up, 2 times 2 times I is positive 4i. And 1 times 3 times j is positive 3j, so we write plus 3j. And remember, our formula is diagonals down minus diagonals up. So that gives us I plus 2j plus 6k minus, in the parentheses, k plus 4i plus 3j. Then we distribute our negative to our second parentheses and combine like terms. I minus 4i will give us a negative 3i. 2j minus 3j will give us a negative j. 6k minus k gives us positive 5k. And so this is the cross product of vector v times vector u. Now look at what we got our answer for this for b compared to our answer in a. Look and see what happens. I wonder if that normally happens or if that's unique. Now let's try vector v cross product with vector v. So again, set up your determinant I, j, k. First, second row would be the coefficients of vector v, which is 3, 1, 2 if I'm doing I, j, k. And the same thing again for the second column. Now copy down our I column and our j column. And then remember it's diagonals down, so the product of that diagonal down is 2 times 1 times I, which is 2i. The product of the next diagonal down is 6j, positive, so plus 6j. And our last diagonal down will give us 3k, or positive 3k. Now let's do our diagonals up. 3 times 1 times k is positive 3k. 1 times 2 times I is plus 2i. And 2 times 3 times j gives us positive 6j. Diagonals down minus diagonals up. 2i plus 6j plus 3k minus 3k plus 2i plus 6j. Distribute our negative to our second grouping, our diagonals up, and combine like terms. So 2i minus 2i will give us 0i. 6j minus 6j will give us plus 0j. And 3k minus 3k gives us plus 0k. Now notice all our coefficients of our I, our j, and our k are all 0. This is called the zero vector. Try a few other vectors and see if you take a cross product of a vector times itself. Do you always get the zero vector or not? Let me know. Now you know how to do various operations in vectors in space or 3D vectors, as well as knowing how to find the cross product of two 3D vectors. Thanks for watching this video. Pick like and subscribe so you can be updated when I have new videos related to mathematical topics.